Okay, off we go. So here's where we were last time. We were looking at this weird question, admittedly odd question to want to ask, of thinking about the amount of fluid sort of nearby a curve, right? And then asking this weird question of to what extent is that fluid overall as a whole moving along the curve as opposed to perpendicular to the curve. Strange question. And sometimes we ask strange questions because they have shockingly relevant answers. That's how it works sometimes. And what we worked out last time, again, you can just look at each little piece of fluid, and for each such piece, you can look at it, well, what is the component of its velocity along the curve? And you can then literally add that up over the entire curve with an integral. And what we find is we actually get a pretty useful interpretation of vector line integrals, right? So a vector line integral is most of the answer there, as it turns out. Now there's this little asterisk, and this is annoying. The area of this cross section. Well, of course, the more area, the more fluid. The more fluid, the more the fluid is flowing along the curve, right? So the fact that there is a factor of A in here is, I'm going to say, expected, right? And also kind of, arbitrary in the question. And so it really makes sense to talk about, per unit area, right? Let's get rid of the stuff that's obvious, right? And what's really nice about this then is that per unit area, I guess I should do this in purple. The rate that the fluid is flowing along the curve, in other words, the answer to our question, right, per unit area is the line integral. So we have ourselves a new interpretation of vector line integrals. And just as a reminder, we started all of this with the idea that, let me get back up. Here it is. We started all of this with the idea that you can interpret a vector line integral as representing work, and that's in the context of where the vector field represents forces. Right? We now have this new interpretation that a vector line integral can be thought of as, and again, it's the answer to this weird question, to what extent is the fluid flowing along the curve, this in the context of where the vector field represents the velocity of a fluid. Okay, now there's a special case of this that is particularly important, as it turns out, and so we're going to entertain what happens when we restrict our attention to a closed curve. And it turns out, it's hard to see this coming, by the way, but later today, we're going to find a shocking application of this idea, or a shockingly surprising fact about this particular special case. Namely, when you're talking about a curve that starts and ends at the same point. In that case, and let me get back to the consistent with the colors. This integral here is called circulation. It's going to be really important. One of our major objects of study in chapters 6 and 7, circulation. But don't lose sight of what we already know. We kind of already know what this is, and that is it's a vector line integral. It's the extent to which the fluid is flowing along the curve. That's what it is. But if you think about it, if you're looking at the extent to which the fluid flows along the curve, and if the curve goes all the way around, and I drew this all the way around as if it's around a circle, and I guess it doesn't have to be, but even if it's not a circle, if you look at its direction vector, if you look at that unit tangent vector always makes a full loop and goes around literally in a circle, right? The direction vector goes around in a circle. Then what that means is the extent to which the fluid flows along something whose direction goes around in a circle is kind of like saying to what extent does the fluid go around in sort of in little circles. And so that's the big interpretation here. And let me look at this first example. Let's start by looking at what the fluid is doing. Let's say there. The fluid is doing like that. And then it's kind of going around like this, and then it goes like that. Well, what is the curve doing at these points? The curve, otherwise known as the dx vector, and by the way, let me circle the vector field here. The curve at nearby points is doing kind of the same thing. So when you look at this dot product, when you look at f dot dx, and you're measuring the extent to which the fluid is moving the same direction the curve is, you're also kind of measuring the extent to which the fluid has a kind of a rotational aspect to it. Okay, and thus the name circulation. It's a pretty natural choice of words. Okay. Now, coincidentally, it happens to be in this case, and this is a flashback to chapter 3, it also happens to be in this case that if you look at a flow line of this vector field that I've drawn, right, a flow line also goes around in a circle. Notice the conspicuous absence of the term flow line anywhere on this page, right? Flow lines are not the definition of circulation, right? It's about the extent to which you have a flow along a curve, and that curve goes around in circles, but the vector field doesn't have to. And you remember we saw an example back in chapter 3 where there was a vector field where all the flow lines were straight lines, and yet there was circulation, right? We computed a curl, and it was not zero. So please don't make the mistake of falling for this idea that it's got something to do with flow lines. It doesn't. It's not about flow lines. It's about what we talked about before there. Now, a convenient point of view on how to sort of visualize this, how to sort of imagine this physically, is to imagine little small objects. And so, for example, if I were to think about I'm going to recall the metaphor I used back in chapter 3. If I were to imagine a little leaf, this being fall, I'm going to use orange. This leaf sitting here floating. Imagine if the water underneath it that it's floating in were flowing per this vector field that I have drawn. What do you think is going to happen to that leaf? Well, it's going to start turning, right? And this is a really nice way to think about circulation. Circulation really does kind of suggest to what extent are we pushing the leaf to make it rotate. And I like to think of it as in two dimensions, as I have drawn here. I like to think of circulation as describing how little bitty, tiny little leaves would spin in the water if they were floating in that fluid. Okay. All right. Now, another important observation: circulation is not just about the fluid; it's about the curve that you're sort of comparing it with. So let's look at this same fluid now, right? The same exact vector field here. Same exact vector field. But now I want to ask, what is the circulation of that vector field along now this curve? Right? And let's just for emphasis, let me draw the tangent vectors. Nearby tangent vectors there. To what extent is this blue fluid flowing along in the same direction that this curve with these green tangent vectors is going? And well, it's not. It's going the wrong way, right? The curve is going to the right. So effectively, when we ask this circulation, we're asking, given what this curve is, given the curve that we're comparing the fluid to, when we compute this circulation, we're asking to what extent is this fluid rotating clockwise, because the curve is going clockwise. And the answer to the question, looking at this blue fluid, to what extent is this blue fluid rotating clockwise? Well, it's negative clockwise because it's counterclockwise, right? So as you would imagine from these dot products, which of course look as they're drawn there, those dot products would all be negative. This vector line integral would be negative, and the circulation will be negative. Everybody on board? Okay. All right, so again, hard to see it exactly coming why we would care so much about this thing, but it was going to turn out, and again, later today, fingers crossed, I hope we'll make it, we'll see what happens. really important object of study. Okay, last little diagram that I have here. Sometimes it's really not obvious what's going on. So, for example, at this point here, the curve is going sort of that way, but notice the fluid is going sort of that way. But over on the other side, the curve is going that way, and the fluid is also going that way. So we've got a weird sort of like tug-of-war between opposing contributions. We have positive contributions coming from over there, negative contributions coming from over here. Sometimes it's not, as, ideally sort of perfectly, symmetrically, exactly lined up as in these first two examples that I like to start with, just to, get the ball rolling, get the ideas, as clear as possible. Most of the time, you're going to have conflicting contributions like this. And so, as it stands, it's really not clear for this one whether the circulation is positive or negative. And we'll talk in a little bit later today, about how we might be able to get our hands on actually answering that without actually just straight up plug and chug computing that line integral. Okay. All righty. How we doing? Pausing for questions. Everybody all right? Okay, I am all about convenient tricks. I love the little convenient tricks. Combination of reasons, not least of which is, again, I did plod my way through an entire physics major as an undergrad, and I had to compute so many integrals, and I saved myself tons and tons of time by way of convenient little tricks. I've already showed you my favorite one being symmetry arguments. Right? This is another one of my favorite tricks, as in this saved me massive amounts of effort, and I think it will save you massive amounts of effort in an engineering major as well. And that is, think about the geometry. Heads up on the geometry. Sometimes the geometry is super convenient and will save you massive amounts of trouble. So, for example, let's think about this vector field here. I got ahead of myself. Let's think about this curve here. Now I've described this curve to you in a weird way. I've given you spherical coordinates as functions of time. That's weird, right? We've never really done that before. But I make the observation, if you have the spherical coordinates, you can plug into the formulas. You can find the rectangular coordinates as functions of time. This is just one step away from a parameterization. But let's take a moment to recognize what a horrifying parameterization that would be, right? I mean, rho sine phi cosine theta would be a monster, right? And I'm scared of that. I don't know how to do integrals involving that. Terrifying. So crazy, crazy curve. And then let's look at this vector field right here. And, okay, I mean, that's not so bad, I suppose. But still, with the curve, oh my gosh, that's outrageous. And we want to compute the vector line integral, it says, of this vector field over that curve. And again, looks terrifying. Turns out this is super easy. This is do it in your head simple, as it turns out, with a couple of cool geometric observations. So the first geometric observation, look at this right here. Rho is always 1. Rho is always 1. We're always on the surface of the sphere. And now just geometric appeal, but if you're always moving around on the surface of the sphere, then your velocity is always tangent to the surface of the sphere. Geometric appeal. If you're on a surface, your velocity is tangent to the surface. And so your dx vector, if I look at this dx vector right here, that dx vector is always parallel to the sphere. So there you go. Let me highlight that. So the dx vector there, parallel to the sphere. Okay, now let's look at the vector field real quick. What can we observe about that geometrically? And I'm going to notice that it is a scalar multiple of the position vector x. Scalar multiple. Now, not a constant scalar. Sure. It depends on x and y. Could have depended on z, but it didn't, but whatever. But anyway, scalar, independent of whether it's constant or otherwise, that is a scalar multiple of the position vector. And the position vector, of course, is always perpendicular to the sphere. Wonderful feature of spheres, right? You got to love spheres. They have all sorts of cool geometric features. This is one of them. And that means that our vector field is always perpendicular to the sphere. Let's see here. Let me highlight like so. So if I'm interested in, now let me get rid of my distractions. If I'm interested in, and I forgot to highlight the, there you go. If I'm interested in this dot product, f dot dx, I'm interested in that dot that, one of which is parallel to the sphere, one of which is perpendicular to the sphere. Those two vectors are perpendicular to each other. And when you're taking a dot product of two things perpendicular to each other, you will get 0. In this integral, we are adding up a bunch of zeros, and that adds up to 0. So really quick, now I went through a bunch of details in presenting this because it's your first time to see an argument like this. But, once you kind of get used to this style of an argument, you're going to notice really quick when rho is 1 and you're confined to the surface of the unit sphere, that geometrically that tells you cool information. And again, you're going to notice really quick when you see stuff like this, scalar multiple of the position vector, and you can kind of see this kind of stuff coming pretty far away once you get used to this. Yeah?
Can you say again why f is perpendicular to the sphere?
Yeah. So f is a scalar multiple of the position vector. Right? Is that part cool?
Mm-hmm.
Yeah. The position vector, well, here it is. It's the x vector from the origin to your location. And the origin happens also to be the center of this sphere. And now I'm just going to make this observation about spheres, and that is radii of spheres are always perpendicular to the surface of the sphere. So, yeah. And so f being parallel to that, we get the same thing. Yeah. So really powerful observation. Now again, how often is this going to work? Can I do this every time instead of parametrizing? Oh, no, certainly not. Right? This is a 1 time out of 10 kind of a deal. But again, that's super helpful, right? If you're facing down the, bazillions of integrals to have to do, and you can knock out 10% of them with clever observations about geometry, you just saved yourself, 100 skillion integrals. It's pretty cool. Yeah.
Would this work if rho wasn't 1?
It would work if rho is any constant.
Okay.
Yeah. So we do need it to be a sphere, so the geometry of the sphere is really, really important in this argument. So yeah, if rho were 3, totally fine. But if rho were some formula, then yeah, that's out the window and we're in trouble. Right.
So
right. Yeah.
The surface has to be uniform.
For this specific argument that we're making here, we're critically using the wonderful and unique properties of the sphere exactly, right? And I don't want to say that you should only look for awesome geometry with spheres. There's a different awesome geometry for planes. And there's a different awesome geometry for, other kinds of surfaces. It's a pretty short list, to be fair. But the moral of the story here is, when you're looking at a surface that has some cool geometric symmetries, keep your eyes open for possible awesomeness. Yeah. Okay, so moving along. This next one is something I have to do. I don't like having to do this. It is ultimately this is kind of a liability for us, I think. I think it'd be fair to say. So there's a notation that is in common use that I therefore have to show you. And the reason for the notation is fairly accessible, and so I feel like I need to show you the reason. Ultimately, it's going to end up giving us a notation that I don't have any intentions of going out of my way to use because it doesn't help in the context of Math219. So there are some good things to say about it. I'll get to that in a moment. But anyway, here we go. innocent observation. We already knew this. We can write out x prime in coordinates. I can take this dt and kind of distribute it. And then I can ask the reasonable question, what should I call this thing right here, x prime dt? And I feel like dx is hard to argue with as a reasonable notation for x prime dt. And likewise the dy and likewise the dz. Okay, so with that observed, here's what you can do. I'm not saying should, right? Here's what you can do. If dx is dx, dy, dz, and if you have some vector field, well, it's going to have coordinates and common notation, weird though this may seem, whatever, but anyway, it's pretty common to call those coordinates p, q, and r. You can take this vector line integral, write it out in coordinates, like we've done here, and then just kind of manually write out the whole dot product there, and it turns into this. You everybody see what happened? Now, whether we like this or whether this makes sense or whether this has got geometric utility for us, yeah, separate questions. But does everybody kind of just see what happened, good or bad? Yeah? Okay. So, yeah, so this is actually a very common choice of notation to take this, what my sort of personal favorite notation in Math219 for vector line integrals, and we can rewrite it like this. All right, now why would I want to do such a thing? Let me start with the negative, which I think is pretty clear. It's bulkier, right? It takes a lot more to write down. So that's weird. I don't care for that. Here's another complaint, and a little bit more sort of substantial complaint. If someone were to ask me, okay, well, yeah, but what about this PDX? What does PDX mean? Does this mean something physical? Right? Let's pretend our vector field is a force. And so this is a computation of work. What does PDX mean? Physically speaking, not really anything particularly helpful is the thing. It's an arbitrary portion of the work computed with respect to an arbitrary choice of coordinates. It's not really physically all that natural. So that's pretty unsatisfying. Where, by contrast, if you look at what I see here, what is F? That's force. That's a physical thing. What is dx? That's displacement along a little piece of curve. Physically and geometrically natural. I know these. I understand what these look like. I can see them in the statement of the question. This is, I think, intuitively satisfying. Not so much with this also bulkier notation on the right. Okay, so that's the negative. So now to the positive. Why does anyone like this notation? That's actually got a pretty good answer, and that is that this notation is basically the notation for what's called differential forms. And differential forms are a really, really important idea. Powerful math can be done and can only be done with differential forms. It is super good stuff. Now, that said, it is well beyond what I think is appropriate in this course. We're not going to do any differential forms in this course. But if you want to know why some people like this notation, this is why. Differential forms are totally awesome, right? And depending on the situation, depending on what level of math I would be doing, I would absolutely use differential forms in certain contexts, for sure. So it is a good notation. As a result of that, it is in common use. And you are going to see this, right? Whether I like it or not, right? In the context of Math219, we don't have much use for it. But outside of Math219, you're 100% going to see this, right? So you're going to notice some homework exercises are written in this notation. And that's, I think, to prepare you for the fact that in your future, outside of Math219, you're going to see this notation in books and other contexts. So when you see that notation, what I encourage is make sure to remember sort of where it comes from, and remember this dx, dy, dz all together, that's just kind of coordinate expansion of the dx vector. And related, the p, the q, and the r all together are just giving you the coordinates of the vector field. That is your integrand. Right, so that's the way you interpret. When you see this notation, kind of reverse this argument, and you can reverse engineer what's your f, and you can reverse engineer the f dot dx notation. Is everybody on board with that observation? All right. Okay, moving along. Symmetry theorems. Good news. For scalar line integrals, notice the theorem as I've written it here looks exactly like the theorem as I wrote it in when we were talking about double integrals, and the theorem as I wrote it when we were talking about triple integrals, and I deliberately write it as analogously as I can because the theorem is truly analogous. This is basically the same idea. It's true for basically the same reason as other theorems that we've seen previously about reflections over lines and reflections through planes. So, good news. It comes with the same two warnings because, again, it's morally the same theorem. So be careful with all the usual disclaimers and warnings that I've made previously, and have fun. Symmetry theorems are awesome. Now, very importantly, though, the bad news. This is only for scalar line integrals. Only for scalar line integrals. If you try to write down an analogous theorem for vector line integrals, it doesn't work. It crashes and burns. There is no odd symmetry theorem for vector line integrals. And if you make an argument about odd symmetry for vector line integrals, well, you're writing down nonsense. And again, nobody wants that, right? None of us want that to happen, right? So be careful about this, please. Don't try to make these arguments for vector line integrals. Now, why doesn't it work? Well, it has to do with the unit tangent vector that is inside of a vector line integral. And keep in mind, this is an alternative notation for vector line integral. So that unit tangent vector right there, let's try to apply this now to this curve, which I have attempted to draw as being symmetric. I think it's reasonably okay. It's symmetric over this line. I can do better than that. Close enough. And let's think about what that unit tangent vector looks like. And is that unit tangent vector is it the same on both sides? Nope. Is it opposite? Maybe. Maybe that's the part that's opposite. Nope. It's just different. And this is just not going to work. Right? And specifically, if you were to think about, for example, a vector field, let's say a vector field that looks like that, maybe that's your F. If it were odd, then its value at the reflected point would be like that. And now I ask, rhetorically, looking at this integrand, is that dot product the same as or the negative of this dot product? No, not even close. They're just totally different. This dot product on the left is pretty large. This dot product on the right is pretty small. They're unrelated. So no such theorem. And that's too bad. So anyway, disappointment, but that's how the cookie crumbles. Questions about that? Everybody all right? Okay, so that's section 6.1. We're going to move on now to section 6.2. 6.2 is going to be our first venture into a different world. There's some totally awesome theorems here in Chapter 6 and Chapter 7. The big reason why chapter 6 and 7 are so important, right, is called the vector calculus theorems. And there's, depending on how you count, several of them. And again, depending on how you count, there's arguably 6 of them. Arguably 7, depending on how, you want to look at things. And they are all a little different, but they all have certain things in common. And it got noticed very quickly when mathematicians first started discovering these theorems in the early 1800s. They started to notice these theorems look a lot alike somehow, but in different geometric contexts. And it took mathematicians something on the order of about 100 years to actually formalize and figure out explicitly how to say exactly what it is that they have in common. It was fairly recent math that did this. So anyway, that is very, very sophisticated stuff. Couldn't begin to show you that in this class, so fear not. I'm not going to throw a bunch of scary, sophisticated stuff. What I am going to do is try to present these theorems all from a sort of parallel points of view, because then even though you don't actually see the scary ideas, you'll see the punchline, the benefits of those powerful ideas without the scary. Okay? So I am going to present all of these theorems from a certain point of view. The first couple of things that I'm going to do here about Green's theorem are not going to directly be about Green's theorem. They're going to be about the overall point of view that I want to push on all of these theorems. So the next couple of pages of discussion are very general. Okay, so here we go. So let's. I just want to define some terms. What do I mean first by a quantity on areas? What I mean is, if you give me an area, then a quantity on that area is a rule that allows me to give you a corresponding quantity. It's as simple as that. So, for example, if you give me a two-dimensional region, we can talk about how much mass is in that region. That is a quantity defined on that region. You give me a different region, there's a different amount of mass, right? So the amount of mass depends on which region are you talking about. So that's all I mean by a quantity on areas. Is that reasonable? Could be mass, could be the area itself. Could be the perimeter, right? Any number that we can define, by some sort of a rule for any region. All right. Make this observation here. They don't have to be physical, right? I mean, very often we like to think about physical stuff because y'all are engineers, and it's totally cool. And we think about mass and stuff like that, tangible, concrete stuff. It doesn't have to be. Okay, next little definition. I've used this term a lot. I'm going to finally get around to writing down exactly what we mean. And I've been saying this over and over again, right? The whole is the sum of the parts. That's all we mean here when we talk about a quantity as accumulating over areas. An accumulating quantity, right? Again, you've heard me say a million times. It just means the whole is the sum of the parts. So, for example, just as a sort of a silly example, if I were to look at this whole area here, and ask how much mass is in that whole area? Well, if I were to look at how much mass is on the left and how much mass is on the right, right, and add those up, right, the mass on the left plus the mass on the right gives me the mass in the whole. Well, of course it does. Right? That's how mass works. That's how are we going to say that? It's just how mass works, right? I hope that's intuitively satisfying. Right? Population, likewise, right? If we were to look at some region of land and ask, okay, how many people live over here? How many people live over there? Add those up, and you get the number of people that live in the whole. So accumulating quantities, important idea. Areas accumulate. Again, pretty clear. But I like to point this out as an example, an important example here. Not everything accumulates. Perimeter does not accumulate. The perimeter of the whole is not the same as the sum of the perimeters of the parts. It's just not. Everybody see what I'm talking about? So accumulation is a nice feature. Accumulation is actually a really important feature of quantities. But you cannot assume that it's true. It's very special when that actually happens. Okay. Is everybody are we doing okay? Everybody's quiet? Okay. All right. Right. So, and just a quick clarification. I do specify over areas. Specifically, it's the areas. You know, we're looking at a two-dimensional region of area on the left and a two-dimensional region of area on the right, and then the two-dimensional whole that is their union. So specifically, it's the areas that we're splitting up. It's the areas on which we define the quantity. And so just to be completely precise, we're talking about here accumulation over areas specifically. And it's a little confusing because you look at this perimeter and you think, well, yeah, but perimeter's not an area. Correct. Perimeter is not what we're accumulating over. Perimeter is the quantity. It is the two-dimensional regions that we're asking if it accumulates over, because it's the two-dimensional regions that we're splitting up. And it's the two-dimensional region about which we're asking about the whole and the parts, etc. Okay. Oops. All right. So next, now this is a little bit of a weird idea. There's going to be several moments in this course. This is kind of one of the first ones where I'm going to invoke the following idea, and that is that if it looks like a duck and quacks like a duck, it may or may not actually be a duck, but you can treat it like a duck because it behaves like a duck. And it doesn't really matter if it is a duck. It behaves like a duck, so we're going to treat it like a duck, and nothing's not going to be any problems because it's effectively got all the features of a duck. So that's a big idea. We're going to do that a lot. It allows me to take ways of thinking about things that might not be letter of the law technically true, but they're very convenient, and they will always lead us in the right direction. So this is the first example here, and that is that if you have some accumulating quantity, again, not just a regular quantity, an accumulating quantity, one of these special quantities, the whole is the sum of the parts, you can think of it as actually physically distributed over the area, even if it isn't physically distributed over the area. So, for example, let's suppose that we have some area like this region right here, and there's some task that we have to do. Maybe I have to, maybe this is the bottom of somebody's swimming pool, and I have to, repave the bottom of the pool or something like that. And the question comes up of how much work does it take me? How much work do I perform in picking up all the cement or whatever it is? I've never done this. I don't know how that works. But there's going to be a certain amount of work that it would take to perform a task that would happen over that area. I don't think of work as being physically located in a place. But it behaves as if it is. In other words, if I were to ask, what's the total amount of work that it takes to pave this pool surface? Well, I can compute first how much work does it take to pave that little square, and then next, how much work does it take to pave that little piece of the area, and then how much work does it take to pave that little piece of the area, and I can add them up, and it is an accumulating quantity. The whole is the sum of the parts, and that will give me the right total amount of work. And so when I am asking these questions specifically, when I'm saying, hey, how much work does it take to perform the task assigned for that little area, if I were to just say I'm going to pretend that the work is in that area, I'm still just going to argue that the whole is the sum of the parts, and it has that feature because it's an accumulating quantity, and it's actually okay, perfectly fine to think of the work as being physically located in that little region, even if it isn't. It's a weird thought. Y'all okay with that? A related idea. Let's suppose that this is a flower garden, right? And I've got to weed the flower garden. And the question I want to ask is, how much time will it take me to weed that flower garden? Well, the amount of time it would take me to weed each individual region, if I add up all those amounts of time that it takes me to weed each individual region, I would get the total amount of time it would take me to weed the whole garden. Is time physically located in a region? No, of course not. That's not how time doesn't have a place, right? But if I were to, just for the purposes of convenience of just how to visualize, if I were to think there's a certain amount of time, it's as if it's in that region, then I could just say, yeah, hold the sum of the parts, and again, I get the right answer. So, a little bit weird, turns out to be very convenient. So the punchline here is that accumulating quantities may or may not actually be physical stuff, but they behave as if they are physical stuff that physically, literally is in those regions. Okay. Alrighty, now here's the upshot of that. If you have stuff, you can talk about the associated kind of density. Right? Now, the obvious notion of density that you all have seen many, many, many times is the idea of mass density. And, of course, that means mass per unit area. And if you want to talk about density at a particular location, you take a limit. And in the limit, that gives you the density as a function of location. And we've done this a bunch of times previously where we've talked about density as literally a function of location, density at individual points, indicating pretty much nearby regions, appropriately small. The smaller, the better. The density is just telling you how much mass is in the region per area of the region. Right? Old idea. Likewise, population density, except now it's people per unit area instead of mass per unit area. And now here's the weird one. We can talk about work density. Very strange. We don't think of work as being in a region. But I remind you, we can choose to think of it as being in a region. If we have chosen to think of it in the region in that sense, then we can talk about how much there is per unit area, and thus the idea of work density, right? And here's the really weird one, the one that just really kind of hard to digest. If you're, again, weeding your vegetable garden, and you have some indication of how much time it's going to take you to pull the weeds per unit area, you can talk about time density in the sense of, okay, per unit area, how much time does it take you to weed that area? That makes sense in terms of the algebra. Is everybody okay? All right. And of course, what do we do with densities? Densities are what we multiply by areas to get quantities, whatever your accumulating quantity is in question. Okay. All right. Okay, so putting everything together. When you have an accumulating quantity, the whole is the sum of the parts. Old news, right? We've written stuff like that down a million times. Again, my little superstition, doff of the cap to the importance of the idea of accumulation. I always like to write down m equals integral dm just to kind of get the ball rolling. And then, as we've written up here, Let's see if I can get this all on the screen at the same time. With dm being density times dA, what we get is an integral, right? I can compute a quantity with an integral of a density. Quantities are integrals of densities. And this works for any accumulating quantity. So for example, a little bit of a kind of a strange idea here, but if you're interested in the accumulating quantity called work, right? And if you've got this idea that work is the whole is the sum of the parts, and you ask about individual pieces of work, and on individual pieces of work, it's work density times area, right? Then punchline, and this is starting to get a little weird here, but work is an integral of work density. Physically counterintuitive, but very convenient in terms of how to write down answers to questions as integrals. Right? This idea of a density is super useful. Okay. And then likewise, if you wanted to compute the total amount of time, and again back to the weeding of the vegetable garden, flower garden, whatever, time would be an integral of time density. Very strange. Okay. All right, so I'm going to make the observation that these could be thought of as theorems, right? So these two statements that I have here could be thought of as theorems. The fact that they hinge on an accumulation motivates calling these accumulation theorems. And I think it's a pretty reasonable thing because these are a couple of accumulation theorems. Related, semantical argument, they all kind of hinge on this idea of a density. So you could call these likewise, you could call these density theorems. And depending on my mood, I could use either one of these terms, whatever is, both of these ideas are critical to writing this down, right? Anyway, reasonable points of view there. All of these theorems that we're writing down here, they all effectively come out of one single property, right? This comes from the idea of density, which comes from the idea that these quantities behave like physical stuff, which comes from the idea of accumulation. Anytime you find a quantity that accumulates, you have a corresponding accumulation theorem. That's a really powerful idea, right? So many different quantities accumulate, and we've got accumulation theorems for all of them now. Is everybody on board? I know this might seem like sort of silly abstraction, but this really is going somewhere. Okay. All right. Okay. So, important ideas for a lot of stuff we're going to be doing. By the way, I did all of this in 2 dimensions, but you can just as well do it in 3 dimensions. We can talk about quantities accumulating over volumes. That's where, again, the whole is the sum of the parts, where you're splitting up volumes. And likewise for one-dimensional domains, single variable integrals. Okay. All right. So, where this is going is toward one particular surprising example. There is a particular accumulating quantity about which we're going to write down an accumulation theorem, yawn, right? All of these accumulation theorems are kind of, we've written down bunches of integrals where it's an integral of something, and that something is a density. Doesn't seem very exciting, but there is a particular, very surprising example of an accumulating quantity that results in a really powerful theorem. And we're almost to it. I don't think we're quite going to make it because we have like 2 minutes left. Last thing I want to do real quick is just talk about what I mean by the word boundary. Y'all have probably previously understood the idea of boundary as, very reasonable. Let's try to get this all on the page. A boundary is just, sort of the edge. It's the border. It's the dividing curve between set and not set, right? Here you're in the set, here you're not in the set, and the line between them is boundary. Right? No more. Boundary, very importantly, now is an oriented thing. We have to attach an orientation to boundaries. From this point in the course on, the word boundary always means an oriented thing for all of the rest of chapter 6 and all the rest of chapter 7. Boundary is oriented. And it's oriented according to a very specific convention. It's kind of arbitrary seeming. In fact, no, let me edit that. It is straight up arbitrary. But it is a convention. It's highly standardized. And it goes like this. Wherever your region is, when you're looking at the boundary curve, when you say the word boundary, boundary means oriented specifically in the direction such that as you go in that direction, right, here's my little finger, man, right, this, as I walk along like this, as I'm going in the correct direction of the boundary orientation, the region's on your left. That's the rule. Always go whichever way, puts the region on your left. Totally arbitrary. Why the left? Why not the right? Somebody made a decision 150 years ago, right? It's the standard, it's convention. Doesn't matter. Could have, if they had done it the other way, math would have still worked out, right? But this is the standard convention, and we have to stick with it. So in this scenario here, that's the direction you go to have the region on your left. But notice, on this region here, which way do I go along the boundary to put the region on my left? Well, I would have to go that way. So you can't oversimplify. You can't treat this as, oh yeah, always move to the right or always move to the left. No, it's not that simple. You need to move whichever direction puts the region on your left. And it's also tempting to call this counterclockwise, right? Notice here, all the different directions that I have to go along this boundary to put the region on my left. They're all counterclockwise. But not over here. Right? That's the direction I go at that point to put the region onto my left. But I'm going clockwise. So please do be careful about that. Yes, true, for nice, what you might call solid lumps with no holes in them, then yeah, sure, counterclockwise. But heads up for scenarios like this. I'm sorry, I lost track of time. We'll draw the line right here. See y'all later. Have a good one. Don't forget about attendance if you came in after. See you later.